So our objective for this lesson has been to derive a power series for a function, and we've done it in a variety of ways. Like we've started with geometric, done some kind of algebraic manipulation in order to turn it into the power series or the function in question, right? We also learned that whenever you have a power series, it's continuous and differentiable on its interval of convergence. So this brings us to the last way to form a power series for a function, and that is term-by-term differentiation or integration on a series you're already familiar with. Just remember that when you take the derivative or the integral of a power series, it keeps its radius of convergence, but it may not keep its interval of convergence because it may lose or gain an endpoint. You have to check them. Okay, so let's start with example 10. And when I say start, how can you possibly say start when we've already done 9 examples prior to this? Find a power series for f of x is equal to the natural log of 1 plus x. What? Have we even done natural logs so far? Haven't we been just doing like rational functions? Actually, we have done natural log, but it's been in disguise and you didn't recognize it. Maybe you will by the end of this episode. So, since this is all about taking the derivative, what happens if we take the derivative of this f of x function? Well, it's a natural log, which is a u prime over u. So the derivative of the natural log of 1 plus x is just 1 plus, not 1 plus, 1 divided by 1 plus x. And that, hopefully you recognize as a function that we found a power series for at the beginning of this lesson. It is the summation from n equals 0 to infinity, negative 1 to the n times x to the n. So let me ask you a question. How would I go backwards in order to find f of x? Remember, we just took the derivative in order to get this power series, so I need to take the antiderivative in order to go back to the natural log function, the original f of x. That's what we're going to do. Now, of course, we introduce a constant of integration when we do that, but since we know what the natural log of this function is, like this natural log of 1 plus x, we would have an initial condition that we could plug in and solve for that plus c. Let's see that happen. Okay, so we're going to start by taking the derivative of this function, 1 over 1 plus x, right? And then treating this thing geometrically as 1 over 1 minus a negative x. Its first term is 1. Its constant ratio is a negative x. So it gets written as a power series from n equals 0 to infinity of a negative x to the nth power. You can rewrite this negative x to the nth power as a negative 1 to the nth power, x to the nth power. So far, so good. Now, let's go ahead and take the antiderivative of that so that we can work backwards and find the original function that we're looking for. So, speaking of the original function, that is the natural log of 1 plus x should be equal to the antiderivative of the summation from n equals 0 to infinity, negative 1 to the n, x to the n with respect to x. Okay, all right. So I'm going to come back up here just for a second and let's just kind of expand this out so we can get a handle on what the series looks like. So remember that our first term was 1 and then our common ratio is a negative x. So we multiply it by negative x, multiplied by negative x again, multiplied by negative x, and so on. Okay. So whenever I go to find the antiderivative of 1 is just going to be an x. So we can still start here at 0. This is equal to, oh yeah, I would have the plus c, right? So I remembered finally, where did that just go all the way to the beginning? Oh my God. All right, look at all of this that we've done and all of this that's still left to do. That's actually pretty close. We're pretty close to the end. All right, where did we left off? I don't even remember. Okay, antiderivative. I remembered to write down my plus c before all of this started. Okay, so still have my summation from n equals 0 to infinity. And this thing is unaffected. We're only taking the antiderivative with respect to x. So I still have negative 1 to the nth as the alternator here. And x to the n plus 1th power over n plus 1. Okay, so if I were to expand that thing out, let's see, this would be a c plus antiderivative of 1 is just an x. Oops, an x. Antiderivative of negative x, the negative x here, add 1 to the exponent, divide by it, should be a negative x squared over 2. And this one, x to the 3rd over 3. And then minus, I'm assuming, an x to the 4th over 4, and so on, right? I point that out because now we're going to use our initial condition in order to solve for c. Initial condition, what are you even talking about? I wasn't given one. Well, I can select one because I can evaluate what would be really easy to evaluate here for f of x. If I stuck in a 1, this would be the natural log of 2. But what happens if I stick in a 0? This would be the natural log of 1 plus 0, which is the natural log of 1. I can do that. So here, I'm going to say that this is the initial condition. We have x is equal to 0. So f of 0 is equal to the natural log of 1 plus 0, which is the natural log of 1, which is 0. So in other words, you have the point 0, 0 on your function. I'm going to plug 0 in here for all the x's. All of these x's are going to disappear because I put zeros in for them. I'm left with c on this side is going to be equal to 0. Do you need me to write that out? Just in case. I plug in, the whole thing's supposed to be equal to 0, and I have c plus a 0. Well, why'd that go up there? 0 minus 0 squared over 2 plus a 0 cubed over 3 plus, okay, you get the point, right? So in other words, our c is equal to 0. So we just solved it, and then, hey, that thing just disappears. So here, let me rewrite some stuff. Actually, no, I'm not going to rewrite it. I'm just going to go right up here and just take it away. Take it away. So really, like, our first term here is just x. And what we ordinarily do is that we rewrite this thing. Since this is the first term, this is like, what would happen if I stuck in, whoops, like this as an n equals 1 instead of an n equals 0. And this one would be an n equals 2, and this one is an n equals 3, right? It's a heck of a lot more elegant here because now this is to the first power over 1, this is to the second power over 2, to the third power over 3, but that is going to affect this guy over here. So essentially we are translating this n value to the right one. So when we translate to the right one, we're going to subtract 1 from each one of these exponents. Think of SRT transformations. So this becomes our summation from n equals 1 to infinity, negative 1 to the, subtract 1 from your n, subtract 1, x to the n over n. Dun, da, da, da. So we have just found a power series for the natural log of 1 plus x right there. So I'm going to recap that because it's super, super important. Not only that is it super important, it is going to go on your memory card. You should have it memorized. The natural log of 1 plus x is equal to the summation. We're going to go ahead and start this one at 1 because we translated it. 1 to infinity, negative 1 to the n minus 1 power x to the n over n, which is equal to, as we saw right here when we expanded it out, x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and so on. All right, what's left to find? Well, you always need to find an interval of convergence for these guys. And to find that interval of convergence, we'll have to use the ratio test. So the limit as n goes to infinity, absolute value of, add 1 to your exponents. Whoa, 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 whoa. Anybody pick up on this? I just did. Anyway, negative 1 to the n plus 1 minus 1, it's to the nth power, x to the n plus 1 over n plus 1. multiplied by your reciprocal, so you'll have n up top and -1 to the n minus 1 on the bottom, and then x to the nth, boop. And let's cancel stuff. Like, get rid of these altogether. X to the n plus 1 divided by x to the n is just an x up there, but the n's stick around. It's just what they do. So the limit n goes to infinity of n over n plus 1, absolute value of x. Limit of that guy is 1, and then we keep our absolute value of x and force it into being less than 1, which means -1 is less than x, which is less than +1. Yes. And we just have to now check our endpoints. And I am running out of room, so I need an extra page. Man, this looks so familiar. Have we already done this? Probably on the last exercise. X is equal to a -1 whenever I plug that in here for our summation. N equals 1 to infinity. I would have a -1 to the n minus 1 power, also -1 to the nth power, and then over, where we got, was it just n? Yes, okay. And then simplify here because we can add our exponents. We have an n plus, this n plus that n makes that a 2n minus 1. So a -1 to the 2n minus 1 power over n. So you might think that this is alternating harmonic, but it's not, because what kind of numbers are these right here? 2n minus 1, no matter what, this thing right here is an odd number. And if it's an odd number, that means you're always raising -1 to an odd power. It's always going to be -1. Always. No matter what, it's -1. So you could think of this as a negative of your series, 1 over n, and that 1 over n is harmonic, which diverges, which means that you just lost that endpoint. We don't have that one. Okay. And then let's try the one over here on the right-hand side. Maybe we get that one. So, n equals 1 to infinity here, -1 to the n minus 1, and this one's just going to be 1 to the nth over n factorial. This guy right here does a whole bunch of nothing. Those don't combine, right? Because that's a +1. So I'm just going to get rid of it. And then we have ourselves the alternating harmonic series, which converges, so we do get that endpoint. So here is what our interval of convergence is from -1 is less than x, which is less than or equal to a +1. All right. So I'm going to do a little bit of an extension on this thing before we take a look at the next little exercise. And that is the fact that, remember when we talked about the alternating harmonic series, which is basically what, let's see, this guy is right here. Because of this, we should be able to now find the sum of the alternating harmonic series. Now remember that the alternating harmonic series is conditionally convergent. We're going to find the sum for it, and then Riemann said that, you know what, you can rearrange the thing and you can get any sum that you want to. So since this is equal to a summation from n equals 1 to infinity, -1 to the n minus 1 over n is equal to the natural log of 1 plus, well, what did we stick in there for our x value? We stuck in 1, right? So basically, we're just saying that's equal to the function that we have right here. And then 1 plus 1 is equal to 2, which we get the fabulous result of the sum of the alternating harmonic series is the natural log of 2. That's amazing. Now then, let's go back up here to the fact that our series is alternating. It is an alternating series, which means that we could, whenever we go to evaluate, say the natural log of, I don't know, let's say that it's the natural log of 1.1, for example, we should be able to approximate it very, very easily with an alternating series, and then figure out how far off we are with the alternating series remainder, the error. That's what we're going to do right here, this last exercise for this video, but it's not the last exercise overall, of course. Use the previous power series to approximate the natural log of 1.1 using the fourth partial sum. This guy right there. Okay. So fourth partial sum, that just essentially, yeah, easy for you to say, essentially means that you're supposed to use just 4 terms. So here's what it would look like. Oh, no, actually, I have this animated over here. That's what I'm going to do. Right there. All right, so here it plugs in. So again, you have the function f of x is equal to the natural log of 1 plus x. Essentially, we plugged in a 0.1 to get the natural log of 1.1. So your x value is 0.1. So there is the series expansion. Remember, this is x squared over 2 plus x cubed over 3 minus x to the fourth over 4. Here's your 4 terms. If you sum this up, there's your fourth partial sum. You could calculate that by hand if you really wanted to, or throw that thing into the calculator. All right, since this is a alternating series, we should be able to use the alternating series remainder in order to see how far off we could possibly be. All right, alternating series remainder, remember, is always less than or equal to the first neglected term. The first neglected term, since we went up to 4, must be the fifth term. So the fifth term would be 0.1 to the fifth divided by 5, which looks like this. And then you can go ahead and work this thing out at 0.1 to the fifth power. You could turn that into probably some scientific notation to make that a little bit handier on you. Look how accurate we got. With just 4 terms, this is our error. So incredibly accurate. And essentially, this is a way that, this is the whole power or the usefulness of these power series in order to approximate a function like natural log. Like, how would you find the natural log of 1.1 otherwise? Well, power series gives us a way to approximate it very, very quickly and very, very accurately.